ran away, they left it behind, I don't know. It was an American guy who found it. He took this home as a souvenir. And then the guy who found it died 14 years ago. So when he died, this machine was sold. And actually, I'll do this. So this machine was sold to this guy, a man called Simon Singh. I don't know if you know Simon Singh. He's an author. He writes science books. They're very good. This one here, this one's the code book. This is about Enigma codes and things. It's a very good book. But Simon owns this machine I want to show you. So let's go back to the video. So I want to show you how this machine works. Now, if this does work, my assistant here is going to help me. So I'm going to open up the machine, show you the insides. So it looks like this. Now, it's beautiful inside. It's 1930s technology. It's wood, it's steel, it's silver highlights. It's a beautiful thing. It's pretty much like a typewriter. So it's essentially a typewriter. So I'm going to show you how it works. I'm going to send you a message in code. Now it should be something in German. It should be a message about Bratwurst or Spitz or something. Schadenfreude, something like that. But I'm just going to keep it easy. I'm going to say hello to you. I'm going to say hello in code. So I'm going to type H in the message here. H becomes Z. There you go. And the code lights up. So H becomes Z, it lights up like that. But I'll do the rest of the word. Hello is the word, so E becomes Y. If I continue, if I do L, hello, L becomes I. If I do the second L in hello, L becomes Y again. And I'll finish this with the O. O becomes X. There you go. And that's the code. Now the machine doesn't send the code. Someone has to stand next to you, look over your shoulder, write down the letters that light up. They write it on a piece of paper, and then they can send that piece of paper, whatever letter. You may have noticed something weird about that code. So if you notice the two L's were different letters in the code. So if I do this again for you, what I can do, I'm going to do this in a second. My assistant here, I'm going to press the letter K. This does work. And K becomes Y again. Now if I keep pressing K, it's different every time. It's a different pattern every time. There's no pattern to that. There's no way to know what it's going to be next. So you can see why they thought it was unbreakable. This is a very difficult code. Difficult every time. So let's see how this works. What I can do, I can open this up. I'll show you the insides of this machine. If you see them, you might see them in museums. They're in glass boxes in museums, so they're difficult to see. But this is the inside of the machine. Things to notice. We have rows of lights. There we go. And then 3 big wheels here at the top. Now the big wheels are called rotors. Inside the rotors is full of wires. And imagine all the wires inside. And all the wires are crisscross, mixed up. They're like spaghetti. Imagine that all the wires all mixed up inside. Now look what happens. When I press a letter, the rotors turn. This rotor moves when I press a letter. Every time. When this does a full turn, and you may have just seen it happen, when this does a full turn, it kicks the middle rotor forwards of this. When the middle rotor eventually does a full turn, it kicks the left rotor forwards one place. So you have a fast rotor here, a middle rotor, and a slow rotor. There you go, kick. It's like hands on a clock. It's like having a minute hand, hour hand, second hand. So they're going at different speeds. That's the idea. Now, these rotors actually come out. You can change the order of the rotors. You can swap them. And there's something to show you up front. So down here, which is difficult to see, we have wires down here. I can show you there. So wires at the front of the machine. And one of these wires will connect a letter. We have the alphabet here. We connect a letter to another. So you might connect the letter A with the letter T. It makes a pair of letters. Those two letters will swap over. That's another level of scrambling. There's even more scrambling at the front of the machine. I might be able to show you a better idea of this in a second. Now, it's quite a clever machine, but I can describe how it works. In the top right corner, that's the battery. It's a battery with a light. So when you put a battery with a light, you make a circuit, it lights up. It's very easy. Here's the clever bit. The wires are inside here. When the wires move forwards, the battery gets connected to a different line. And it changes. So let's do it like that. If I do this again, move these wires forwards, and this battery will connect to a different line. I might be able to give you a better idea of this because on my computer here, and I hope this will work, so I'll put that. On my computer here, I've got an Enigma machine simulator. Right. So you can Google for this, download this, you can play with this. You can have an Enigma machine at home. It works just like the real Enigma machine. Send secret messages to your friends. Now, if I press a letter, let's see what it does. If I press E, then E becomes F. So it lights up. So it makes a code, but I want to show you this. If I click this button, I'm going to show you the wires inside the machine. If you remember, I said the wires were like spaghetti and crisscross. That's what you're going to see now. This might look complicated, don't worry. Alright? This is the inside of the machine. And it is. All that is wires. All those are wires. So look what I did. I pressed the letter E, follow the yellow line, press E, and you go through the machine. It scrambles, 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 loop back. It actually goes through the machine again in reverse. Go back through the machine, and then connects to E. And, oh sorry, F lights up. But if I keep pressing E like this, I keep pressing the same letter, the wires move. So E becomes U, then the wires move, E becomes S, then the wires move, E becomes H. So the path of that yellow line changes each time. So you connect to a different letter each time. That's why it's a changing letter. Right. We need to get the message back. Let's get the message back again. This is no good if we can't decode the message. So let's decode the message. So I'm going to do another message here. A quick one, short one. So I'm just going to say hi. Right, so HI, that's it. So 2 letters, HI, I do. So that's my message. So first of all, I need to close the machine here. And I'm going to type in the message hi. I'm going to make a code, and then I'm going to decode the message. Let's see if I can do that. So hi, first of all. If I press H, H becomes B. So it's B in the code, and L becomes, oh sorry, I becomes L. There you go. I anticipated it. So I becomes L. So BL is the code. You write down the message. You send the message. Over here, far away, on a ship maybe, a German officer receives the message. They get a code. It says BL. They've got an Enigma machine as well. Now their machine is exactly the same as this one. One thing I have to do. This rotor here moves forwards 2 places when I say hi. If I move it back 2 places, I reset the machine to where it started. If I reset it back to where it was, I'll type in the code. B becomes H, and L becomes I. And you get the message back. So it's code and decode machine. Type a message, make a code. Type the code in, get the message back. Brilliant, fantastic, wonderful. It's a really clever machine. It's just a lovely piece of engineering, really nice. Now, these 2 people who are far away from each other, each have a machine. They have to be set the same. How did they know how to set the machine? That was written down for you. On a piece of paper, you had instructions on a piece of paper. It changes every day. So for every day, you would have instructions that tell you how to set the machine. I'll show you what it looked like. This is a code book or a key sheet, piece of paper. It looks like this. So this is it. So on the left here, if you can see, that's the date. So it changes every day. I want to show you how this works. So this first column here, with the Roman numerals, so that is, do you remember there are 3 rotors? Rotor 1, rotor 2, rotor 3. They can change order. So this tells you how to set the rotors. So here, rotor 3, rotor 2, rotor 1, in that order. So these are instructions. This, I haven't talked about. The rotors are labelled on the outside. They have labels either 1, 2, 3, 4 or A, B, C, D on the outside. Those labels move. You can turn them. And there are 26 ways to set each label. If you change the label, it changes the setup. So you need to know where to put the labels. That tells you the instructions for the labels. So 26 ways for that one, 26 ways for that one, 26 ways for that one. Actually, let's write this down. How many ways can I order 3 rotors? 6. How many ways can I set these labels? 17,576. This one, those are pairs of letters, you can see that. Do you remember the wires at the front of the machine? It was a wire that connects one letter to another in a pair. Those are the instructions to set your wires, to connect which letter to which. So follow those instructions. 6 pairs of letters here. How many ways can you set that? Now this is just for the military. They were very proud of this. There's a large number of combinations. It is 100 billion ways you can set those wires. A huge number. And this is something called the ground setting. That's the rotor, pretty much, the rotor starting place. Each rotor has 26 starting positions. 26 for the first one, 26 possible for the second, 26 for the third. How many possible starting places? That's another 17,576. How many ways to set the machine altogether? To do this altogether, and I'll tell you one thing, I am allowed to ignore this. That's just the label. That doesn't change how many settings you have. It just changes how you label things. So you can ignore that one. But how many settings does it have altogether? 10,000 trillion. There are 10,000 trillion ways to set this machine. Right? A huge number. You can't check all the possibilities. Now, there is one more thing I have to tell you. Because every day there would be dozens or hundreds of Enigma messages every day. If every message had the same setting, that would be about security. It would help, it's a clue, it would help you break the code. So they didn't do that. Every message had its own secret setting. It did one extra step. Every message had its own secret starting position. Those 3 rotors can be set to its own starting place. The operator would pick a starting place. But he has to send that starting place to the other person. So he would send it at the beginning of the message in code. Let me show you how it works. You have to send a secret setting. So you've got your Enigma. You set it to the ground setting. That was on the instructions. For example, let's say you set your machine to X, Y, Z. The operator picks his own secret setting. He might pick ABC. Why not? Okay, he's going to send ABC in code. He types it into the Enigma machine and he makes a code. He actually does it twice. So ABC, ABC. And he makes 6 letters in code there. So in this example, JTEQGF. 6 letters in code. He sends it at the start of the message. At the other side, over here, the other person uses his Enigma machine to decode those 6 letters. He gets ABC, ABC, and then he knows that's the secret setting. And that is the setting to use for the rest of the message. Right, that's a lot. That's a lot. But you have to do that. Every message has its own secret setting as well. It is a lot, I know. Right, the first people to break this code were the Polish. So the Polish were doing this. The Polish were already trying to break this code. 1932 they started, so long before World War II. They knew Germany was a threat. They were trying to break this code. Do you know what's nice? Before this time, codes were more like a language problem. It's a language skill. For the Enigma was a technological problem. It needs a technological solution. So they started getting mathematicians to do this. So they started to recruit young mathematicians. This is one of them, Mariuszewski. Now, oh, this is fantastic. This is a great story. People don't tell this story, it is so good. Right. The Polish mathematicians were able to work out the Enigma wiring without seeing the Enigma machine. Just from the codes, they were able to reverse engineer the machine. What they did, Yevsky here designed a series of equations, mathematical equations, to work out the wiring. From the codes, he was able to do this. Now, to finish the job, he needed some extra information. He needed some information to put into the equations. He needed some of those code books I showed you, those Enigma settings. Now, to get those, they needed help from a spy. So they got help from this spy. So this is Hans Smith. So he was a German spy. So Hans was from a rich family, but Hans himself was not doing well. He was down in his luck. So Hans had a brother, and his brother was a general in the German army. And his brother got Hans a job. And part of Hans' job was to destroy secret Enigma material, secret Enigma code books. However, instead of doing that, he would sell them to the French. And then the French would pass them to the Polish, and right, that's exactly what they wanted. That's the information they needed. They put it into their equations, and they could work out the wires inside the Enigma machine. Remember, without seeing the Enigma machine. And then they could build their own replicas. So some people talk about this story, like we had to steal a German Enigma machine to find out how it worked. Not true. Not true. We didn't have to steal a German Enigma machine. We knew how it worked. We worked it out. We worked it out. Even better. That's even more impressive, I think. So the machine was never the mystery. The mystery is what is the setting they're using. It changes every day. That's the mystery. Not the machine, but what setting are they using today. You have to do this every day. Now, that's what we're going to do from now on. Now, to cut it short, throughout the 1930s, the Polish code breakers and the German code makers are having a battle of minds, a battle of wits. So German code makers make it better, more difficult. So the Polish would have to break the code. And then the Germans would make it better. And the Polish one, they have to start again, they have to break the code again. So this is constantly happening. And then I'll skip to this point here. Then Yevsky designed this machine, Bomba. This is a code-breaking machine that the Polish made. Some say this is named after a type of ice cream. Some say it's named after the ticking noise it made. And some say it's a good a name as any, it'll do, it's fine. Now, this machine works like simultaneous Enigma machines. You might be able to see, there's some spaces here. So it's like Enigma machines working away. And you need one of these machines for every rotor order. Now you remember there are 3 rotors and there are 6 ways to order. So you need 6 Bomba machines, one for each. And then the Germans improved security again. They added 2 extra rotors. So now they have a box of 5. You pick 3 from a box of 5. There are 60 ways to do that. So now you need 60 Bomba machines, 1 for each order. They can't do that. They can't stretch to that. They didn't have the resources to do that. And that's when they contacted the British. So 5 weeks before Poland was invaded, only 5 weeks before, they had a secret meeting between the British code breakers and the Polish code breakers here in Kabaki Woods in Poland. Secret meeting, and the Polish passed to the British their information and those replicas as well. And the British continued their work. Now, in a not very subtle way, I have to bring this back to Alan Turing. I haven't talked about Alan Turing for a bit. I'll bring it back. So, meanwhile, in the 1930s, Alan Turing is at university, so he was studying maths. He graduates in 1934. He then starts doing a Master's of Maths. And this is the year that he decided to take on one of the great unsolved problems in maths. So, at the beginning of the 20th century, a mathematician, I've got a photo of this guy, a man called David Hilbert, a German mathematician, set a number of challenges to 20th century mathematicians. And part of these challenges was this thing, a problem called the decision problem. And I'm going to try and give you an idea of what the problem was. Hilbert wanted to know if there was a general method, a general algorithm that can tell me whether a mathematical statement is true or false. Wouldn't that be good? So it could tell me if I can prove this thing. Now, they didn't know how to prove it. It was a big unsolved problem. So Alan Turing decided to try it. Now, Alan Turing, to say maths, his brains and bullets. And so, in lieu of a better punchline, I might leave it at that. I'll say thank you for now. We might do some questions later, but I'll say thanks again.
Thank you, James. Maybe some questions here?
Yeah, I won't keep you forever, don't worry. I will let you go. But maybe 2 minutes, and we'll do a couple of questions.